Today, I'm going to walk through the difference between total load and net load, or another way to think of this is your coil load versus your space load. But really, to demonstrate, I'm just going to walk through the fundamental steps in HVAC design and explain the interplay between loads and airflows. To demonstrate this concept concisely, I'm going to use a very simple system here. It's a ventilator with heating, common in large industrial spaces or warehouses, and this is going to handle the heating load for my space. So the first thing we're going to do is calculate the heating load in the space. We'll call that QS. The load components we need to compute include our external load. So this is really going to be the conduction through our walls and our roof, slab, windows, our envelope load in the winter, and our infiltration sensible load. This would include outside air that makes its way into the space directly, and we're looking at the sensible portion of it only. That brings up the question, why are we looking at the sensible load only? Aside from the fact that it is in the winter and typically latent loads are not considered in winter conditions because it's so dry, but this concept applies to cooling too. Why are we looking at the sensible load? The reason is because the load in this space is being conditioned by air that's going to be blown into the space. And you cannot handle the latent portion of the load through your supply air. You need to extract moisture to handle the latent part of that load. And that can only happen with a dehumidifier or with a cooling coil that drops the air below dew point. So that's not something that happens through supply air in the space. That's something that would happen up at the coil, at the unit, or in a dehumidifier if there is one. Okay, so let's say we've added up these load components and our space heat load comes out to 100,000 BTUs. This is what we need to handle to maintain a comfortable set point in the space. We're going to use this 100,000 BTUs to determine the amount of airflow, CFM, being supplied to the space. How do we do that? For simplicity, we can use our sensible load equation, 1.08 times CFM times the leaving air temperature, that's our discharge air, minus the indoor air temperature, which is our space set point. We specify a discharge air temperature, let's say it's 100 degrees Fahrenheit, and we specify our set point, let's say that's 70 degrees Fahrenheit. And reworking this equation, then we can rework this equation to solve for CFM, and plugging in our variables for space heat load, leaving air temperature, and indoor air temperature, we come out to 3,080 CFM. So we've just calculated how much airflow at 100 degrees Fahrenheit we need to blow into this space to maintain 70 degree set point given these space heat loads. This QS is our net load, but it is not our total load. Our total load applies to this coil. And the main question is, how hard does this unit have to work given the configuration that it's in to accomplish this net load in the space? For this example, this unit is bringing in 100% outside air to condition this space. And let's say the outside air temperature is equal to 0 degrees Fahrenheit. We actually don't have to do a bunch of other load calculations to get to the total load. We already have all the information we need. We know how much CFM, 3080, needs to come out of this unit. We know what temperature that airflow needs to be at, 100 degrees Fahrenheit. And so we, again, can use the simplified heat load equation to calculate this total load. This time, Q total is going to be equal to 1.08 times our CFM. But this time it's going to be our leaving air temperature minus our outside air temperature. Solving for this, we get a total load of 332,640 BTUs. That is the actual total load on this coil to meet the conditions that we've set up here in the configuration that's been set up for this system. Now, I showed you a very simple system setup, but the same concept and the same steps apply for a more complex configuration. So let's take another example. This time we're in cooling mode and we actually have return air going back to the unit. It's going to mix with our required amount of ventilation air. The coil is going to be handling that, and it's still going to be reaching a certain discharge temperature. So the same steps apply, where first we calculate the space cooling load. And this time, instead of just external and infiltration sensible, we'll also be including the internal load component from people, lights, equipment. And again, it's the sensible portion we're concerned about because of what I explained a moment ago. We're going to calculate our space sensible cooling using these components. Let's say that comes out to 50,000 BTUs. Again, we're going to use the sensible heat equation to find our CFM. Except this time our delta T is going to be our 70 degree set point minus our 55 degree cooling discharge temperature. Solving for this comes out to, coincidentally, 3,080 CFM. I'm then going to plug this CFM in up here to solve for my load on the coil. The main difference with this configuration when solving for your load on the coil is instead of just taking the straight outside air and conditioning that down to 55 degrees, you need to first solve for air mixing. So when the outside air mixes with your return air, you're going to get a mixed air temperature. Your mixed air temperature is going to depend on your outside air temperature and your return air temperature, typically close to your indoor air temperature, and the airflow ratio of each. So if this is a 50-50 mix, outside air and return air, then our mixed air temperature is going to be about 85 degrees Fahrenheit. Using these variables, we can estimate our cooling coil load using the same simplified heat equation of QT equals 1.08 times CFM. And this time it's going to be the difference across the coil, which is our mixed air temperature minus our leaving air temperature. And this comes out to 99,790 BTUs. Just remember, in this demonstration, I'm using the sensible heat equation. So we just estimated the sensible load on the coil, and this does not include the latent load on the coil, which would also have to account for the humidity, the wet bulb in the airstream, not just our dry bulb. So in both examples, I hope that gave you a better understanding of what the total load is when compared to what the net load is in the space. Or you can think of it as coil load versus space load.